and giving me the opportunity here to talk about what I would think is hopefully a useful resource or general purpose resource for laterality research. So let me just set the stage a bit to really get the gist of what I was trying to do here. Generally, when we think about what we're doing as researchers, we are obviously in the business of creating knowledge. And I think it's only fair to remark that knowledge is typically not only dependent on, but also constrained by the observations that we make. These in turn, these observations, are completely dependent on our research questions or agenda, as well as of the methods that we're using. In this regard, I see all kind of research being best characterized within these three dimensions. So there are some conformative studies, for instance, starting with literature suggests that something might be true, and we set out to test that. So this is our typical hypothesis test. We can have some exploratory studies, so which regions are, for instance, asymmetric in schizophrenic patients, as well as some predictive studies looking into structure-function relationships, for instance, and trying to predict out-of-sample participants, which we haven't seen before. And these different goals of research methods are best characterized or described in two different forms of methods. So either conventional statistics on the one hand, or machine learning on the other. And I don't think we need a laterality consensus to have consensus about the following sentence. I believe that it's generally good to have diverse ideas and many different perspectives in research. So let's look, for instance, at the corpus callosum, which René typically calls the most beautiful structure in the brain. We can look at the corpus callosum from an anatomical standpoint. So here you see different anatomical sections of the corpus callosum. Other people have looked at it from a geometrical standpoint, such as the Wittelson parcellation, which we already heard something from. Aboitis has looked into histology, looking at diameter size, which is obviously important when relating callosal diameters to conduction velocity. Other people have obviously done some connectional work where we are doing, for instance, tractography and trying to understand what regions within the callosal midsection link to other regions in the brain. And I could obviously now talk about the many other people that work in this field or that are interested in the corpus callosum, such as Roberto Caminiti, Eileen Lydos, or of course René Westerhausen. But these people are very well established, and it's my talk. So let me show you one of my other studies on the corpus callosum, where we basically used the first principle gradient from resting state fMRI, which is a derivative or a measure of functional hierarchy, in order to get an idea of the distribution of fibers within the corpus callosum that link to different heteromodal or homomodal processes. So obviously this is all nice and good. We get small pieces of a puzzle, and we got a better overview of the entire puzzle with this. But there are obviously also some biases that can be based on the priors that we're setting, so on the research question. For instance, in a study here, where we looked at structure-function relationships in white matter, which was headed by Stephanie Forkel, we did a systematic review, identified 326 studies in neurology, psychiatry, and healthy patients. And you can already see some tracks are more popular than others with regards to their respective fields. What I, as a laterality researcher mainly, am more skeptical about is the following number. So here you see metrics, this is all fine and good, but look at that. 14 studies out of these were not interested in the hemisphere. They didn't matter, it didn't matter for them if the tract is on the left or the right side. Instead, they just merged the two tracts and pretended it was one, which is obviously kind of ridiculous when you think about it. So this is an obvious bias. The bias also becomes apparent when looking at the number of studies looking into different functions. For instance, obviously, I'm just pointing out the corticospinal tract, which most of us will associate with motor cognition. But did you know that at least some studies found relationships with language or executive functions? This might obviously be some form of publication bias, but it also shows the lack of interest. Same is true for all other tracts we looked at in this study. So let's now look at hemispheric asymmetries and try to identify the priors that we are typically working with when asking the question, what in the brain is asymmetric? There are different brain representations that we could look at. For instance, we can have some geometrically defined regions or functionally defined regions. We could look at some white matter tracts by some tract atlas, or use a method such as TBSS. Regardless of the method, all of these have the following in common. In order to identify hemispheric asymmetries, we have some form of defining homologous units from which we extract the variable of interest. This can be volumetry, it can be activity, it can be anything else. And then we typically do a pairwise comparison. So the left entity versus the right entity. And this obviously led to some very interesting observations and findings. So we all are aware of probably the work by Geschwind and Levitsky on the planum temporale asymmetries. We already have seen some work by Kong et al. On surface area asymmetries using the Desikan atlas, also cortical thickness asymmetries. And James has yesterday evening shown us his beautiful study on a new large scale study on population level asymmetries using almost 40,000 participants in the end. But while this is great to understand or to map asymmetries, obviously this comes at a cost with some limitations. I just highlighted that James had around 40,000 participants. I don't know how about you, but I don't have these kind of participants just readily in my closet, right? And maybe for some samples of interest, we simply don't have big databases from which we can derive these statistical powered samples. So we might be out of luck here. And instead, we need to reduce dimensionality because of multiple comparisons by just looking at some single areas instead of the entire brain, which obviously decreases the potential for finding new findings. Also, the choice of parcellation when we're going this route to decrease dimensionality matters because there are multiple parcellations out there. And in the end, such an univariate comparison approach is unlikely to tell us anything about global hemispheric differences. So when we move from local to more global patterns. So wouldn't it be neat to have an alternative approach in which we basically don't need to concern ourselves with issues coming from multiple comparisons, in which we are working irrespective of some parcellations, so decreasing the amount of priors we're having, and an approach that is maybe capable of at least giving us a hint for defining the determining aspects of a given hemisphere. And this is basically what we're trying to set out here. So we try to change the perspective from asking the questions that identify differences between left and right via means of some statistical comparisons towards using the power of machine learning to find features that correctly classify a hemisphere as either left or right. Let me show you the pipeline to give a better understanding of how we did it. So I can already disclaim that we did this in 2 different data sets. What we're doing is we took, in this case, in this proof of principle study, volumetric data. So this is VBM. We aligned the data onto a sample-specific symmetrical template, split the 2 hemispheres, flipped 1 hemisphere so that we've got a near perfect alignment between the left and the right, and set standardized this. We now had 3 different approaches. The typical approach was the univariate comparison, where you would basically use this, calculate some form of laterality index, use a 1-sample t-test, or you can also do a 2-sample or paired sample t-test, which basically gives you the same results. And then you find significant asymmetries. On the other hand, we use what I call a low-dimensional classification. Basically, the idea here is, I won't go too much into detail. So here we used a dimensionality reduction technique called uniform manifold approximation and projection to reduce the complexity of the data in each hemisphere onto 2 dimensions. We then used support vector machine, which is a machine learning classifier, to identify left and right, and we get a certain precision or accuracy. And given that these were already enough complicated words, I'm not going into detail about this approach. But what I will highlight here is our high dimensional classification approach, in which we basically also go from this data, left and right. We then use some form of algorithm to classify a given hemisphere as either left or right. And this will give us a certain coefficient, which we can use to basically ask the algorithm not only what was the left and what was the right hemisphere, how good are you in understanding what hemisphere it is I'm presenting you with, but also what information did you use to correctly classify as either left and right. And this is basically what our feature selection is doing here. As I said, I'm not going into detail with the middle part, but let me show you some results. We used 2 different samples, 1 sample with 226 participants and 1 sample with 216 participants. I'm just showing the top sample, so the first data set now. On the left, you have what could be arguably be the ground truth. So basically the laterality quotient visualized as minus is this time on the left, plus is on the right. For each voxel here presented on surface. Here you've got the results of a t-test that asks what is significantly asymmetric, basically. And we use the threshold-free cluster enhancement method because if I would show you Bonferroni, you would not find a single voxel being significantly asymmetric. I mean, it's like 400,000 comparisons, so I can't blame the algorithm for that. And here you see a very widespread pattern, basically. So almost everything seems to be asymmetric. It doesn't really look like real biology. But looking at our approach, we see some findings that basically asking the algorithm what was left, what was right, what information did you use to come up with this result. We can find some very typical asymmetric clusters that kind of make sense. In order to evaluate this, we compared the patterns with derived from our Bruto selection and t-test here with the laterality quotient maps at different thresholds. And as you can see, if we are very, very liberal, the t-test outperforms our approach. But as soon as we're going higher with the thresholding for lateralization, our approach actually outperforms typical results shown from t-tests, which basically shows some form of complementary results or use cases. And obviously, the average accuracy for identifying a hemisphere was near perfect with 0.96. This is not an, okay, which basically is cross-validated with 5-fold cross-validation. So we have some we have some grounds to believe in these results. I won't go much into detail, but you can see this kind of differs. The results stayed the same. Even in the other data set, we kind of reproduce the patterns we're seeing here. So to summarize real quick, the classification framework that we're proposing works basically based on VBM data. It shows us what I would call determining characteristics of a given hemisphere. I've got this here because it's a tool for you guys, so you can just download that, and I'm happy to help you. But one could now say that's pretty cool. It's a method, awesome. But what is it good for? Like, why do we need that? And here I will talk a bit about an upcoming study where we used our approach in to understand more about comparative neuroimaging. Basically, as we highlighted in a paper I published with a lot of very famous authors 2 years or 1 year ago, we talked about the state of comparative neuroimaging in the primate neuroimaging community. And one of the big challenges is finding homologs between macaque, baboon, human, and chimpanzee. So basically non-human primates and other primates. There are obviously different methods how you could do it. There are, for instance, expansion maps that have been proposed, something based on graph theory, or work by Roger Mars on gradients to actually align different species to one another. But similar to brain size, hemisphere determining features could do the same for us. And here I'm showing our preliminary results, comparing here on top, chimpanzees, here on bottom, the human brains. In blue are leftward asymmetric determining areas. On red are rightward asymmetric determining areas, hemisphere determining areas. And when we now look at this pattern, so basically extracting certain metrics such as voxel count, the mean strength of lateralization, and also the variance of lateralization, we can see that within the chimpanzees, for instance, the right hemisphere always wins. Like, it has higher surface area. The areas have a slightly stronger strength in volumetric asymmetry. There are also more variance. And the pattern is completely reversed when we're looking at the human brain. Basically, we have higher leftward space in the cortex that tells us something about the left hemisphere. We have a stronger lateralization strength within these blue areas, as well as higher variance. So this is just one thing we have done now, and we're also looking at different samples such as Alzheimer's, schizophrenic patients, etc., to really try and prove that this could be an, let's say, at least interesting tool to use. Let me just shortly stop by situating this method into the bigger picture that I showed earlier. Basically, I believe that we kind of managed, or we aimed to develop a machine learning approach that is more situated on the left side. Basically, that can be used for exploratory studies and confirmative analysis. And with that, I don't have much to say anymore. There are lots of people I would like to thank, but for the interest of time, I just highlight Susanne Weiss, who is very supportive in everything I'm doing. And with that being said, thank you very much for your attention. I'm looking forward to questions.
And yeah.
Thank you very much. Very impressive work. And I was wondering, if you go back to the neuroanatomical perspective, what would be the hemisphere defining characteristics? Because if I look at your results and I remember the study from René's lab, there was a very strong asymmetry sort around Wernicke's area, which was conspicuously absent on your slide. So it doesn't seem to be that the asymmetry is defining the hemisphere. So maybe you could take a step back from the computational approach and let us know what this means on a neuroanatomical level.
So as you might know, when looking into literature on like volumetry of Broca's area, or let's more precisely say inferior frontal gyri, pars opercularis, pars triangularis, you will find differences in literature. This has been pointed out by Kong et al. We also pointed out in this study with James Ho, that basically there's no real consensus on whether or not inferior frontal gyrus or Broca's area is more asymmetric or not. There are studies indicating it, but it's not conclusive in my opinion. And obviously, like when you go the anatomical route, we also need to appreciate that there are different like metrics which we could look at. For instance, like volumetry in some form, cortical thickness, surface area, or even going into microstructural differences. And since there are some nice studies by Katrin Amunds showing actual asymmetries in cytoarchitecture when looking at pars opercularis and triangularis. And I think that might be more of a way to really find meaningful asymmetries. But we only did volumetry. So I'm sure the pattern might look different when looking into another metric, which I would gladly do. Does this answer your question? Sorry.
Which structure would be the one that defines the best physical activity?
Okay, so what my results here would show, just talking about volumetry, what is a left hemisphere is not independent of what is a right hemisphere, right? But we're looking at what differentiates the two hemispheres. And in this regard, it would be what our Boruta maps are showing. So our feature selection maps, which are these areas here. So we're seeing within the superior temporal sulcus, planum temporalis areas A1, medial temporal sulcus and inferior temporal gyri areas. We do see some areas here in front which might be reminiscent of pars opercularis. Triangularis, and we see some in the ACC. As well as areas here in, oh gosh, now is this still fusiform gyrus? I'm not so sure, it should be more here, but yeah. So basically this is what we find. It's actually kind of in line with what other people have found before. So we don't find something entirely new. It's just a new perspective, methodological perspective of confirming something that we already know. But the advantage is that this is kind of consistent without having 40,000 participants. So in the actual paper, we also found similar patterns when looking at, when splitting the data with regards to sex or handedness, where we have fewer participants even. So we're not even on 100 participants here. Thanks for your question.
And since I just got the microphone accidentally back, I'm very pleased to see that the superior temporal sulcus is also in there, which is my favorite area. And I'm pleased that you mentioned it as the first area.
Actually, my question has already been answered. I was also not sure if it was a stupid question, but since you said the program needs two hemispheres that it can relate to each other, that's already clear, because I was wondering if it can also, like, if you give it a box of hemispheres,
so
there is no.
So basically, it's I don't want to spend too much time and going too technical, but it's a supervised learning algorithm. So basically, you give it labels for the left hemisphere, labels for the right hemisphere. This is our target variable. and then you give it some feature space, which in our case, in this high dimensional approach, is voxel per voxel. So every voxel in a hemisphere, like every object, basically, every observation is one hemisphere here, will be fed into our algorithm. Yeah, that's basically it. But we can talk more about it later.
Thank you very much. I don't turn around, so I hope there are no other questions. Thank you very much.
Thanks a lot.